Welcome to Getting Started with Elixir by Pact Publishing. Section 5, Control Flow. In this section, you'll be learning about the various ways in which we can implement more complex algorithms and computations in Elixir. We'll explore the concept of recursion, how to implement branching paths using conditional expressions, and how to handle and raise exceptions in our code. Let's move on to the first video, recursion. In this video, we'll define the concept of recursion and learn how to design and implement recursive or looping computations in Elixir. Let's start by revisiting one of our old functions, the factorial function. If you take a closer look at this function definition, you can see that it calls itself repeatedly in order to compute its return value. It only stops when it reaches 0, in which case it returns the value 1. This kind of arrangement constitutes a recursive call. And this is precisely what we can define as recursion. It's a method of dividing complex problems into smaller ones, which are then more easily managed. In the case of our factorial function, we compute the partial factorial values using repeated calls until we find a trivial solution, for which we then can point out the final value. In order to implement a recursive algorithm, we first have to define a base case, the simplest solution for the problem. After that, we define a function or a series of functions that compute the solution, always converging towards the base case. Putting this in contrast with our factorial function, we can see that the simple factorial of 0 function constitutes our base case. The more general function multiplies the number in its argument with the call to itself, with an argument that will converge to the actual base case eventually. Now, let's try to come up with a recursive solution to a different problem altogether. We were given the task of counting the nodes belonging to a graph. A graph can be defined by a series of nodes, the circles in the picture, connected with each other, represented by the arrows. In this case, it's a directed graph, since the connections only flow in one direction. We've defined the structure of the graph to be like so. Each node is a map with a children key containing a list of other nodes to which it has connections to. If the node has no children, it's represented by an empty list. Let's try to come up with the base and general cases for this problem. The base case is pretty straightforward. A node with no children yields a count of 1, which is itself. For the general case, when the node does have children, we count all the nodes of the first child of that node, and then recursively perform the calculation on the rest of the children for that particular node, until the node has no more children, in which case it converges to the base case. Translating this into code is now possible using a function named count that takes a root node from the graph. The base function matches against a node with an empty children list, returning the value 1. The more general function takes the head and tail of the list of children and sums the count of the first child with the count of a node containing the rest of the children. As you can see, the general function will converge to the base case once the tail of the list of children yields an empty list. And this is what the final product looks like inside its own graph module, ready to be used. We've used the shorthand notation for the body of the first function, since it's just a simple one-liner. And we can finally test it and see if it's working. We'll define the graph and assign it to a variable named graph. Passing that variable to the graph.count function yields the correct computation. This is the actual value for the example that was presented. It has a total of 7 nodes. And that's all about recursion. In this video, we've learned about the concept of recursion and how to define recursive algorithms using the base and general case definitions for a problem. We've also seen how we can leverage recursion in order to do the looping computation, which is a very common case in functional programming.